Hello everyone, welcome back to my channel Be an Architect. In the last video, we discussed let and var. We saw that the same let behaves differently for struct and classes. So in this video, we are going to understand the reason behind that behavior. And the reason is not the keyword. It's how Swift models data and where that data lives in memory. This is the part 2 of our memory series, and today we'll connect semantics with memory. Let's start with the core question: why do let structs and classes behave differently? It's not the keyword, it's the semantics of the type, value semantics versus reference semantics. Value semantics means you work with independent copies. Reference semantics means multiple variables share the same object. And this difference in behavior is what we observe with let. Now, to understand this behavior, we need a mental model. Memory is broadly divided into two regions: stack and heap. Stack stores values typically in line, which means the data sits directly in the memory frame. There is no extra level of indirection, no pointer to follow. Allocation is extremely fast because it's sequential, using a simple stack pointer. It follows the principle LIFO, last in first out, and memory is automatically cleaned up when the function exists. On the other hand, heap is used for dynamic memory, where size or lifetime is not fixed. Here, variable stores a reference and the actual object lives somewhere else. Accessing data requires following that reference, which introduces an extra level of indirection. Heap objects are managed by ARC, which tracks ownership using retain and release operations. And remember, this is a conceptual model. Swift compiler can optimize placements using techniques like escaping analysis. So, stack versus heap is not a strict rule, but a way to reason about behavior. Now, let's zoom into the stack. Values are stored in line, which means direct access, no indirection. Memory layout is usually known ahead of time, though generics and existentials can change that. Because of this predictability, allocation is extremely fast and deterministic. Now, when we use let with value types, Swift enforces immutability at compile time. No mutation instructions are generated. The memory itself is not read only, but the compiler prevents changes. This is why value types feel safe and predictable, especially in concurrent systems. Now let's look at the heap in detail. When we create a class, the variable stores a reference, not the object. The object is allocated separately in heap memory. Let me show you an example. So here I have defined a class user. If you will see, I have defined this with a constant and I am printing user. So in the right hand side you will see the address of user. This address is the heap memory address where user is stored. So access happens in steps. First follow the reference, then reach the object, then access the data. Since the objects can be shared, Swift uses ARC to manage their lifetime. Each reference increases ownership, and when no reference remain, the object is deallocated. Now, when we use let with classes, Swift freezes the reference, not the object, because object stores on heap memory and stack is just keeping the pointer of that memory. So you cannot reassign the variable, but you can still mutate the object's property. Now, let's connect everything. Struct follows value semantics. Each assignment creates a new independent value. Mutation is isolated and controlled by the compiler, whereas class follows reference semantics. Multiple variables can point to the same object. Mutation affects all references because the object is shared. Now, one important thing: struct equals stack and class equals heap is a useful mental model, but not a language guarantee. Now, think like an architect. If you want predictable behavior, independent values, and safer concurrency, you choose value semantics. If you need shared identity, centralized state, or coordinated behavior, you use reference semantics. Memory layout affects performance, semantic defines behavior, and architecture is about choosing the right behavior. Keep remember, internally, Swift can even move values between stack and heap using escape analysis. For example, when closure captures variable. So now you understand stack and heap not just as memory regions but as a model to explain behavior in Swift. In the next video, we'll go deeper into ARC, struct versus class, and other important topics on memory. If this video changed how you think about memory, then like, share, and subscribe because we are just getting started. I'll see you in the next one. Thank you.